Welcome to Building an Intuition for Composition. My name is Cy Brand. I'm Microsoft C++ developer advocate, and I have a confession to make. I'm bad at maths. I'm like way worse at maths than you might expect. I did maths all the way through high school, right till the end, and I did okay. I passed just about. And then when I went to university to study computer science, I had to do maths again in my first year. And the course was pretty much identical to the one I'd done in high school. So you'd think that after a year of more studying, I would understand the concepts better, I would have got better, but I actually got worse. And it wasn't just to do with marking schemes, it was to do with sitting and looking at a whiteboard full of mathematical notation and just having my entire brain glaze over. I just couldn't do it. So yeah, I'm bad at maths. But I am interested in maths. I'm interested in all of the concepts which help us in computer science, which make our code better, which make our code faster. Things like set theory, like category theory, abstract algebra. I'm interested in all of these things. So I wanted to learn, I wanted to teach myself these things. So I'd look for a bunch of resources and I'd come across the same problems I had at university. Lots of just mathematical notation, which for some reason I just could not fathom. I couldn't get any understanding or intuition out of it. And I thought this was just me. I'd look at a bunch of Wikipedia articles and brain freeze. And then I saw this tweet recently. I used to think I wasn't smart enough to understand Wikipedia articles on math and computing, and have recently come to the realization that no, the articles are just badly written. Maybe there are some people that these articles work for, but certainly not me. So the point of this talk was to be the kind of talk I needed when I was trying to teach myself a lot of the concepts from these branches of mathematics and just completely failing. I want the kind of talk that I could have given to myself and been like, hey, watch this. It can give you an understanding of how these things can help you in your day-to-day coding without having to build up a bunch of really theoretical mathematical understanding. So I'm not aiming for accuracy in this talk. I'm going to throw a bunch of arrows, a bunch of examples out there to try and help you build up your own understanding of how these things can help you. If you want accuracy, look for a different resource. Maybe not Wikipedia. Before I get started on the real meat of the talk, as I mentioned, I work at Microsoft. We have a bunch of stuff at CppCon, a bunch of announcements. We have 10 talks. So if you have any questions about any of our talks, including this one, please come talk to us at the expo hall. We have a table there. We also have our own room. Feel free to ask your questions, give us your feedback, let us know any issues you have. We also have our survey, as we do every year, which helps us to tune our tools to help you better. And you can also win a copy of Flight Simulator, which is always nice. All right, let's talk about std_accumulate. Std_accumulate is an algorithm which is not in the algorithms header. It's in numerics. It's one of those C++ things, but you may be familiar with it. We can give it a range of iterators and an initial element, and it will sum all of these up. So if we have a vector 1, 2, 3, then we add 0 to 1 to 2 to 3, and we get 6. Okay, fairly straightforward. But we don't just have to use the plus operator. We could, for example, specify multiplies. We want to multiply 1 to 1 to 2 to 3. So we can change the binary operator we're using. This is, in a lot of literature, referred to as a fold. And you can kind of see why. If we have a bunch of elements and we want to accumulate them using plus, we kind of fold this operator over all of the elements until we eventually end up with a nice origami crane or something. Of course, it's not just integers we can accumulate. We can accumulate a multitude of things. For example, strings. This will join together hello and CppCon, which just uses the plus operator on std_string and uses the empty string as the initial element. So we can accumulate ints, we can accumulate strings. We can also implement other algorithms in terms of accumulate. So this example takes input range and a predicate, calls that predicate on every element in the range and accumulates them using logical AND. This is an implementation of std all of, or at least it's similar to all of. All of will short circuit, and this doesn't, but it will give you the same answer unless you're doing something weird. We could then just change the name and flip the predicate in order to get none of, and we could make a few other changes to get std any of. The point I'm making here is that you can implement a lot of algorithms in terms of accumulate. In fact, most of the algorithms in the algorithms header, you could implement using accumulate if you tried hard enough. So if most functions in the C++ standard library are kind of like this screwdriver, it works on flathead screws of a certain size, it's kind of specific, then accumulate is more like a sonic screwdriver. If you're not familiar with Doctor Who, then this is just way more powerful than a screwdriver, can do way more things, work in a bunch of different situations. It's so general, we actually invented our own syntax to do this using variadic templates. And this was in C++ 17, it's called full expressions. So we see something like this, function template, which takes a variadic pack of arguments. Then we can fold the plus operator over that pack using this t's plus ... syntax. So we call this sum function with 1, 2, and 3. Then this will generate a function which looks like this. Returns an int, takes 3 integers, and just sums them all up and uses 0 as the initial element. So let's look in a bit more detail at this accumulate call. So we have an input range, we have an initial element, and we have a binary operator. Now we can change this binary operator from plus to multiplies, but now we have a problem because if you multiply anything by 0, you're going to get 0 at the end. So if we want this to 1. Now this initial element, what we usually want to use here is called the identity element. The identity element is a special element of a set which does not change the other input to a binary operator. Some examples which we've seen already in this talk: for int and plus, then 0 is the identity element because add anything to 0, you get the thing back. And multiplication is 1 because multiply anything by 1, you get it back. String plus empty string, you kind of get the picture. Other examples, set union. If you union an empty set with anything else, you get back the original set. Bool and logical AND. True is the identity element for logical, or it's false. You get the picture. The point is that the identity element does not just depend on your data type. It depends on the pair of the data type and the binary operator which you're accumulating. So that's all I want to say about identity elements. Let's look at this binary operator. Here's the example we had earlier of summing up 10 integers. Now, we could have way more than this. We might want to distribute this data set across some number of cores or processors or computers. We might want to parallelize. And we can do that by splitting up the input, giving parts of it to different computers, and we can use the identity element anywhere which we don't have enough input for. So we can just sum up everything on one machine, and then sum the results, and sum the results back together to get our final result. Great, we've parallelized our computation. What if we wanted to use minus? Maybe a little bit contrived, but this is just for demonstration purposes. Say we want to use minus, we fold the minus operator over and over until we get our result, minus 53. Now, if we try and parallelize this, then we get a different answer. We get minus 23. This isn't great. If we do something sequentially or in parallel, we'd quite like to get the right answer out at the end. And the problem is that doing this parallelization work depends on the associativity of the binary operator. where an associative operator is one where the grouping of the operands does not matter. Or perhaps more concretely, if you have A star B star C for some binary operator star, then that should be the same thing as A star B star C. Okay. There is actually an algorithm which was introduced in C++17 called reduce, and that does exactly this. It parallelizes your accumulation and requires the associativity of the binary operator. It also requires commutativity, but I'm not too fussed about that right now. So what we have is 1, a data type, 2, a binary operator which is associative and returns the same type as its arguments, and 3, an identity element. This turns out to be a really, really common structure which pervades across a whole bunch of computer science and mathematics, and it's called a monoid. Kind of a fancy term, but it works for a very specific, for a very general structure of mathematics. So if you have types you're composing often, you may be able to expose a monoid. And doing so allows you to clearly define what object composition means, to turn binary functions into n-ary functions using accumulate or reduce, and by unlocking parallelism. So here's an example of where if you're looking for monoids, if you're looking for composition, you find it in maybe some unexpected places. So here's an example where we accumulate over a range, and we're just taking the max of the 2 elements. So this is std max element, and we notice that this is a monoid because we're accumulating over it. We have an initial element, we have a binary operator, it's associative. So this ordering forms a monoid over the integers. Great. What about the ordering functions themselves? Can we compose those? Does that make sense? What would it mean? Say we have a session type. Every session has a presenter, has a title, has a start time and a duration. The duration might change, but we try and stick to the duration. We might want to display this information in different ways in very different contexts. So sometimes we might want to sort by presenter. Sometimes we might want to sort on start time or get the greatest or smallest duration. Sometimes we might want to sort on presenter then title. Like I have 3 talks at this conference, so maybe we want to sort alphabetically on presenter and then make sure that the titles are all sorted as well. We might not want to bake this into our type. We might not want an operator less than, which just takes 2 session objects and hard codes in some decision about how to order this type. We want to do this ad hoc. We're going to make decisions at our use case. So you might imagine an interface kind of like this. We could have some function called order by, which takes a member pointer. And that will produce an ordering function, which will order sessions by that member. So you could use it by calling max element with your sessions and say order by the presenter. And that will use our presenter as the thing we want to order on. I'm not too fussed by the implementation of order by. It's implementable. You can ask me how later. Now, what if we wanted to do that lexicographic sort? We wanted to order by presenter, then by title. How would we do that? Well, maybe we could compose together our orderings and produce a new one. It might look something like this. We could say we have an operator bar, which takes 2 ordering functions. Of course, you'd want to constrain this using concepts or something, but slideware. We take 2 orderings and we compose them by returning a new ordering. This ordering is first going to call f1. If f1 does have something to say about whether A is greater than or less than B, then we are going to just return that. This std weak ordering equivalent thing is from the spaceship operator. And if f1 says that they're equivalent, then we're going to return f2. So we first order by f1, then we order by f2. And now we have composed 2 orderings. It would look something like this in the API. we call max element with sessions, and we say we want to order by presenter and then order by title. It's kind of a nice API, I think. We can convince ourselves that this actually does form a monoid by having our identity, which is an ordering which always says that two things are equivalent. And then we can further convince ourselves by trying to fold this operator. And you can see this would work. You might not want to call compose orderings, but this is the kind of thing where if you're looking for composition, if you're looking for monoids, then these things come to the surface. If you'd like to learn more about monoids, I'd highly recommend watching all of Ben Dean's talks. I'd recommend doing that in general. He's at Albino. He's currently in the chat. So say hi to Ben. He has lots of talks on monoids and is generally awesome. In fact, I cribbed all of this slide from one of his talks, where this is some monoids which turn up in statistics. They turn up all the time. You want to parallelize your statistical analysis. If you use some of these algorithms, then you can make the most of that. I love seeing everyone saying hi to Ben in the chat. This totally made my day. Okay, let's talk about this. You're actually at Ben Dean on Twitter. I'm sorry. You're Albino other places. Anyway, let's talk about this. If you're not familiar with circuit diagrams, then maybe you're more familiar with this. It's std transform. Or maybe let's talk about std ranges views transform instead, because we love our namespaces in C++20. The idea is this. Say we have some cats, and we want some cute cats. We always want cute cats. So maybe one way we could do this is loop over all of our cats and call make cute on them and push them back into the cute cats vector. This is one way we could implement this. Another way is we could use transform. We could take our cats vector and we could pipe it into transform and give transform make cute. What this does is creates a view which will call make cute on every one of our cats. And it just kind of expresses our intent a bit better, right? Like here we have a loop. We don't like raw loops. If you listen to Sean Parent, it just expresses our intent a lot better. We have cats, we pipe it into transform, we make them all cute. Great. What about optionals? If we have an optional cat, we could check if we have a cat, and if we do, we call make cute on it, and then we do a bunch of other stuff. Otherwise, we're gonna exit the if statement. But we could do a very similar thing. We could pipe C to some transform. It just doesn't work with std ranges views transform and std optional, but you could implement something like this. You pipe C to transform make cute. If there was a cat, it calls make cute. Otherwise, you get an empty optional. Note this is the same structure, right? Another example. Say we want to get a cat, but it's going to take some time. Maybe we need to go to a shelter, all that stuff. We might want to do some other things while we're waiting on a callback. So we'll do a bunch of stuff, and then maybe eventually we'll call wait, and we'll call make cute on the cat which we got. This isn't great. We're having to wait on our future. We have to care about when we're getting this cat, all that stuff. What we'd really like to do is just queue up these operations. So we could just pipe f into transform make cute. So we say we'll get a cat, and at some point we'll have the cat, and then we'll make it cute. We don't care about when this happens. We just care about the library making this decision for us. We're queuing up or composing operations. And again, this is exactly the same structure we've just seen. So if accumulate is more like a sonic screwdriver, then transform is more like a drill. We're drilling into these contexts to get the values. We don't care about the structure which is built up around them. We just care about changing what's in there. You can imagine if we implemented this as a non-member function. Here's an example of how it could look. You wouldn't actually implement it like this, but just for demonstration purposes. Function called transform, which takes some temple of t. So this could be like std optional of int or std vector of bool if you really wanted. Then it takes a function from t to r. and returns a temple of R. So if we had a std optional of int, and then a function from ints to bools, then we'd get out a std optional of bool. We're maintaining the template argument, but changing the values at it. Okay. Other programming languages might call this map or fmap. What we have is a container of t's and a function which transforms the t's inside the container. But container, this word is used a lot for this construct. It's not that great because it's a future container of t's. It's more like a computational context. It's some t along with the context of we're going to be getting this later. So we could instead say that we have t's in some computational context and a function which transforms the t's while maintaining the context, i.e., if you have a vector of ints and you map them to a vector of bools, we don't want the size of the vector to change. That doesn't make sense. This is called a functor. Again, turns out to be a concept which pervades throughout computer science. No, I'm not talking about the C++ usage of functor, which is quite common, the function object, a structure, a class which has a call operator. This is the term which is used in Haskell, which is then taken from category theory. There's actually an article by Jackie Kay from a few years back on exactly this topic, Stop Calling Function Objects Functors. I would recommend going to read that. It's quite amusing. Along with those, there are some functor laws, which essentially say, here's how your functor should behave in order to not be surprising. So I've tried to show these in C++. One, imagine that we have this ID function, which just takes some argument and returns it back. Doesn't do any modifications. One functor law is that if we have some functor and we transform it using the ID function, we should get the same functor we had out. For example, if we have a vector and we call ID on every single element, then this shouldn't change any of the elements. It should not also change the size of our vector or anything like that. All right. Of course, in C++, there's some more complexities because the interfaces for these things copy and whatnot, but I hope you get what I'm trying to express with this. Similarly, the second functor law is that if we have a functor and we transform it with f and we transform it with g, then that should be the same as transforming it with the composition of f and g. The intuition here is that having a vector which we loop over once to call f on everything and then loop over again to call g on everything should be the same as just having one loop which calls f and g. It shouldn't make a difference. All right, so if you have types you're manipulating the structure of just to change the values, then you may be able to expose a functor. And doing that allows you to abstract away the handling of the context and write code at the level of intent. In fact, looking back to 1994, where the standard template library, this is from a presentation to the standards committee, iterators were one of the main concepts which really made the standard template library what it is. And iterators kind of go some of the way to exposing functors in C++, to the extent that some ranges, or at least most ranges in C++ are functors, right? If we have some input range, then we can transform it. So one very specific call to action I can have is look at your types. Think, is this type a range? Does it have some operator square braces? Should I instead express this as iterators so I can easily transform it? Does it expose anything which is a range? Do I have a function like get nth child, which takes an index? Should I instead expose a children range, which you could then transform if this thing is non-const? Things like that. So think about whether you have ranges in your types, because you might be able to expose functors. All right, let's talk about std ranges views join. say we have two functions, a function which takes a cat picture and makes the cat smaller, which obviously makes it cuter. Then we have a function which makes the cat's eyes sparkle. But this might fail. You know, the cat might have its back turned to us or something. We might not be able to see its eyes. So we're going to return an optional cat picture. And if we can't make its eyes sparkle, we're going to return null opt. And say we have a maybe cat. What we'd like to do is say something like, okay, take our maybe cat, transform it by making its eyes sparkle, and then transform it by making it smaller. Yeah, this kind of expresses our intent, but the problem is we have this make eyes sparkle is returning an optional cat pic. So what we then get is an optional cat pic, which we're passing around. So this won't compile and it becomes a mess. What we can do to fix that is use a join. A join will take, in ranges terms at least, a range of ranges and collapse it into a single range. So if you have like a vector of vectors, it will collapse it all together. And you can imagine how you would do a similar thing for std optional. If you have an optional of optionals, then as long as both of those are engaged, you'll get something at the end. And if either of them are not, then you'll get null opt. So it's a join operation on your optionals. This is fine, but you can imagine that as soon as you start adding more transformations, then we just have to pepper join all over the place. We could instead have some function called and then, or other languages might call this bind, which does a transform and then a join in one call. Make sense? This is the code which we would write if we weren't using transform and then, by the way. You know, we check if we have a cat, then we call make eyes sparkle and we check. If we have a cat and we call add top hat and we check. If we have a cat and we call make smaller, and we're having to handle the context ourselves. We're having to deal with all of this unpacking, whereas we should be focusing on the actual work we need to get done. Futures. Say we have a cat and we want to pat its head and we want to scratch its belly. Now, these are things we might want to do, but they also take time. You know, my cat at least likes head pats to take 30 seconds, a few minutes. So we might want to do other things. We might want to drink some tea or look at Twitter, maybe make some terrible tweets. I don't know. But say we have a good boy, then we could pat his head, then say, then we want to scratch his belly. We don't want to care about unpacking the future. We don't care about when this happens. We just pat its head and we scratch its belly. We want to queue up these operations. We don't care about the context. We care about the values which are going through and the transformations on those values. Another example where this kind of pattern turns up is parsers. You might have heard a parser for things is a function from strings to lists of pairs of things and strings. This might not immediately look like a definition of parser because especially in C++, we quite often use more imperatively styled parser implementations. But this is a way you can build up parsers using functional languages. It looks something like this. Say we want to build a parser which matches a character, then we could return a function which takes some string as input, and then it's going to return all of the possible ways we could parse this character, which is only going to be one. So we check if the input is empty, and we make sure that the first character is the one we want. If it's not, we're going to return an empty list. If we did match the character, then we return the character we matched along with the part of the input we did not use. All right. Obviously, you wouldn't implement this way with std list and everything just for demonstration purposes. And then you could use it like this. You have some input, which is hello, and you can build a parser which says, I want to match H. Then we can assert that if we call our parser on our input, then we're going to have H as the thing we parsed, and LO is going to be the rest, which we did not consume. This isn't very useful on its own, but the real interesting stuff happens when we start to compose these operations. So as a silly example, we could build a parser for true or false by first matching T or F, and then checking if we got T, in which case matching ru, otherwise matching false. Okay, so that you can see we're taking the input from one parser and we're piping it into the other parser. We're not having to deal with any of the additional context of like the things that we haven't parsed, all of that. It's all handled by the implementation of and then. In fact, there's another talk from Ben Dean and Jason Turner called Context for All the Things, where they use exactly these techniques for building up a JSON parser at compile time. So this is an example which they had, which I modified very slightly. I don't want to get into the details of it. I just want to show that you can build up complex parsers using these kinds of interfaces. This one, for example, first checks for a 1 to 9 character, and then for a sequence of 0 to 9, and it builds up an integer representation as it goes along. So transform is more like a drill, then and then is more like a pipe with some duct tape. You know, we can take functions whose return types don't quite match because they have some extra context to deal with, and we can just duct tape them together to really focus on the values which are flowing through the functions and not have to focus on the context. So we have some t's in a computational context, and we have a function which composes operations producing that context. This is called a monad. Now, I'd like to take some time to congratulate myself, because this is one of the few C++ talks where I have not made any of the obvious monad jokes. So please drop your congratulations in the chat window. Thank you very much. Of course, there are also a bunch of laws which say, here's how your monad should behave in order for it not to be surprising. So I ported all of these to C++, and I planned to talk about them a bunch, and then I realized it was really confusing and boring, so I'm not going to do that. If you want to learn more about monad laws, come talk to me later, look them up. Some of it isn't Wikipedia, you know. So if you're manually marshalling data in and out of context to manipulate them, you may be able to expose a monad. And that, similarly to Functors, allows you to abstract away the handling of the context and write code at the level of intent. So one area which monads pop up, which you might not think about, is coroutines. Here is an example which I stole from one of Gornishinov's talks from 5 years ago now. This is a TCP reader function. So it creates some TCP connection, and it then loops over the TCP connection, reading a set amount of data until we're done. Now, this is a synchronous function. You know, connecting to a TCP socket might take some time. Reading from a TCP socket might take some time. We might want this to be asynchronous. So we can transform this code into an asynchronous version by doing something like this. Oops, this. There we go. There we go. Don't try and read this code. My point is it looks horrible. We're having to like dynamically allocate some state. We're having to have multiple nested lambdas, which are parsing stuff between them. And this is using that like and then monadic style, which works really well sometimes and does not work well here. Because it's really turning all of the control flow inside out, and it's a pain. I don't want to write this code. I don't know anyone who would choose to write this code. What if instead we could change our synchronous version into an asynchronous version just by decorating our code? This is what coroutines allow us to do. We write in coawait, and that's going to suspend the coroutine until we get our data. We then change the return type to, it could be a task or some future which supports coroutines. And now we've taken our synchronous code and we've transformed it into asynchronous code purely by decorating the synchronous version. So what we've done is we focused in on all the operations which we wanted to perform, all of the data flowing through these operations, and we've pushed all the handling of the context aside. So coroutines in C++20 are a way of exploiting the monadic nature of asynchronous programming, which is kind of cool. It turns out that they're even more general than you might expect, in that if we have some functions which return optionals, this is some code I stole from Toby Alsop. then we could implement some coroutine handler which works with optionals. And then we could write code like this. And we co-await on F1, we call F2, we call F3. If any of these functions return a null opt, then we're going to exit out of the coroutine and return to the caller. So this is the same kind of thing as if we were piping like and thens all the way down this, but it's just implemented in coroutines. It's kind of cool. So this might look like do notation in Haskell if you're familiar with it. In Haskell, do notation is essentially syntactic sugar for transforming what looks like straight line code into a bunch of lambdas with binds between them. Coroutines get you some of the way there. It's not quite there though. Like this coroutine will get split up into multiple functions on each of those co-await boundaries, but the coroutine implementation doesn't give you a way to get at those functions. You couldn't like run part of a coroutine multiple times, which is required for some monads. So coroutines do allow you to implement some, to exploit some monadic structures, mostly for asynchronous programming, and also for doing this kind of thing if you want to. I wouldn't recommend doing this. It's kind of an interesting thing which falls out of the implementation of coroutines. Another is static exceptions, or herbceptions. This is a proposal from Herb Sutter, which tries to deal with a lot of the problems of dynamic exceptions. Here's an example I stole from the paper. We have a convert function, which is going to convert a string to an integer, and then we have something which calls that and it multiplies it by some other int. So we have this decoration throws. This is not a dynamic exception specifier. This is very, very different. What this throws keyword does is it says, actually, I'm not a function which returns an int. I'm actually a function which returns like a union of an int and some statically known error type, or a variant of int error, or expected of int error, if you're familiar with that, or result from Rust. It's the same kind of thing. And then when we say throw inside a function like this, what we're not saying is dynamically allocate this and then unwind the stack and find a catch handler and all that nonsense. No, this just means, okay, we're going to return the variant type engaged to the error state. All right. Then when we call convert, if we get an integer out, i.e. convert return normally, then it's all great. We're going to continue as we went along. If the convert function threw, as in it returned the error type, then stir multiply itself is also going to return the error type and percolate it upwards. So it's very similar to dynamic exceptions, but it can eliminate a lot of the overhead because the error type is known at compile time. And you might notice this is very similar. In fact, what we're doing is focusing in on the data which is flowing through these functions, and we're passing the handling of the error context aside into the implementation. So static exceptions are a way of exploiting the monadic nature of error handling. Turns out monads are everywhere. It's kind of cool. So this is a proposed paper which the committee is currently looking at. It isn't standard yet. I can see chat talking about this. So yeah, go read the paper. It's really, really interesting. I'm particularly a huge fan of it because it really lets you express clearly your intentions. We just want to write our good code. We don't want to focus on percolating things, and we also don't want to pay for dynamic exceptions. We could, of course, transform this code into normal C++, or at least something which is functionally equivalent by if we change our return type to an expected int and error, and then instead of throw, we return an unexpected. Then we flip the stir multiply to return an error as well. And then the last change we need to make is we pipe convert into transform. It's the same kind of thing. And you could see that if stir multiply was doing something else which could itself fail, then we'd use and then instead of transform. So this is a simple transformation of our C++ code. It's just really surfacing our intent a lot better. So look out for monoids, functors, and monads in your code. Expose them in your API. This allows you to both make the client code clearly express composition and write code at the level of intent. Thank you very much. Before I finish off, I will take questions, so please type them in, and I'll quickly tell you about our other talks we have while you're all formulating your questions. So like I said, we do have a table in our expo hall. Please come say hi. We do also have our survey where you can win Flight Simulator. And these are some of the other sessions we had. Of course, yesterday, myself and Marion talked about all the new stuff in Visual Studio, and Julia talked about VS Code. We had some cool announcements like C++ 20 coroutines and modules are all feature complete. Visual Studio Code C++ is 1.0, which is great. We have talks about static analysis, STL today. Tomorrow I have another talk on dynamic polymorphism with metaclasses and code injection, which I really like this talk. It should be great. And then we have talks from Erica and Nick about cross-platform dev and code spaces, and finally finish off with open source fuzzing. I'm not seeing any questions in the chat or Q&A, so I will assume that I was perfectly clear in everything, but if I was not, please come talk to me. I have a Q&A, the Ask Me Anything session, which is on Wednesday, tomorrow after my dynamic polymorphism talk, so feel free to come chat to me then. And thank you very much for listening. Goodbye. Oh, there are questions. Oh, now I'm seeing the questions. Why did these not pop up before? Jesus. Okay, right. Questions. Sorry. Do we need different overloads of the pipe operator to compose different types of functions differently? Yes. So the definition of and then is very much tied to what your type is. So, you know, for optional, it's gonna check if you have an optional, and if there is one, then it will call it. Otherwise, it will return empty optional. For vector, it's going to have to collapse the vectors together. For future, it's going to have to queue up continuations. So yeah, the definition of and then is very much going to differ on the monad which you are composing. Any comment about bringing the pipe operator for C++? Oh, that's Izzy's paper. Yeah, great, love it. What are some frequent use cases for fold expressions? Basically, when you have, well, one of the times I've used it most is folding the comma operator over things. Like if you have a variadic template and you want to call something on every argument you get, then you can use the comma operator to fold all the calls over that. But then also things like my sum are kind of silly, but anything which you have an operator where you want to collapse all your variadic arguments, that's a use case for fold expressions. Slide 69. Nice. Which one was slide 69? Identity shouldn't be 0, or type should be unsigned, which is slide 69. I'm sure there's a shortcut to go to slide 69, but I don't know what it is. Slide 69. Identity shouldn't be 0 or type should be unsigned. I assume you're talking about a different slide because I have no idea what that means for this. Can we have links to Ben's talk in chat? I assume people hopefully link to Ben's talks. They're great. Is the programming definition of monad equivalent to the mathematical definition? That's a really good question. So the definition which is used in functional programming for monad is derived from category theory, but it's not like, we're essentially taking that definition and applying it to the category of of types in our programming language. So it's the mapping is almost there. Even pure programming languages, pure functional programming languages like Haskell have some holes in there. Like Haskell has this idea of the bottom type for expressing certain things, which does not map into the real definition of a category of types. So yeah, the definition of monad is derived from that in category theory. It's not exactly equivalent because, you know, we're dealing with programming languages which are not pure maths generally. Can you explain the difference between a monoid and a monad? Yeah, so the monoid was the triple of the data type, the binary operator, and the identity element, whereas the monad is the and then function, which can compose functions which are returning things wrapped in your context. So the monoid is for like folding over things and parallelizing data operations, and monads are for composing operations within a context and building up pipelines. Do you think it would be useful to have vocabulary types for monoids, monads in C++? I think that there's some difficulty here, especially in, you know, how we express these things. Like, as I said, for monoids, the identity element is predicated not only on your data type, but also on your binary operator. So you'd need to have some way of like specializing a trait to say, oh, for this data type and this operation, then this is my identity element, which I've seen done. People have implemented this. It's just there's some design decisions there. Vocabulary transform, and then, like I said, these things have been proposed. There has been a proposal for a general monadic interface for C++. I think the author of it had to pull it for, I'm not sure what the reasons were, but yeah, these things have been proposed. There's possibilities. There's a wide design space there. I'm not sure where we'll end up. I think, at least for now, for things like the main types which expose or which should expose these monadic interfaces, they can be added on a case-by-case basis, like optional, expected. These are the main ones which I see. I have a paper which proposes a monadic interface for std optional. Do you find it confusing when things like coroutines are close to monoids but don't quite meet all the requirements? Coroutines are close to monads, not monoids. But yes, like when I saw that Toby Alsop had implemented monadic optional with coroutines, I was like, cool. So do we have do notation? And then I looked into implementing the list monad, where, you know, if you have like a vector and if you have functions which are themselves returning vectors, then in theory you could like co-await on all of these operations and you would just build up a single vector of all of the results. I was like, hey, this could be a cool demo, and I went to implement it and it's not possible because of the way that you can't have access to the sub functions which a coroutine is broken up into. So yeah, I do find it confusing when things are close to monads, but not quite. Is throws like the either monad? Throws is exactly the either monad, yes. Either is another word for the std expected or result or what have you. So yeah, throws is just an implementation of the either monad in the language. Do you have any plans to propose your implementation of TL expected to the standard? So I have an implementation of std expected, which has an extended monadic interface. Since std expected is still not in yet, I don't know what the plans are. Like JF knows that my extensions exist and things like that. So yeah, I'm not sure where that's going to end up. For now, you can use my TL expected. Slide number may have been off by a few. Okay. I guess I'm looking for that identity thing again. I'm not going to do that. If you can compose your question in a way which will jog my memory, then maybe I can answer. But yeah, I'm not sure. What's your favorite monad? Oh, I don't know. I think the writer monad was the first one which really made me understand what's going on. The writer monad being essentially something which keeps an audit trail of your functions. You can like write into a string which will accumulate some information, like logging information about the functions you've called. So yeah, I'll say writer monad because that's the one which made me have my like light bulb moment. Do you think it's worth striving for pure functional programming in C++, or would you suggest using functional programming concepts to augment the typical imperative style? I think it depends on the context. It depends on your constraints and the behavior of your types, and of course on a bunch of things which are more sociological problems than technological, like how much legacy code you have or code you cannot change from other people. I think that striving to work in a pure functional style in C++ can help as long as you're not being dogmatic about it. Trying to make sure that your functions don't make changes to mutable state and things like that can help in so many situations. So I think it's very useful to always have in the back of your mind when you're designing and writing code, and not necessarily being like, we have to write everything pure functional. That just ends in tears. There are some good libraries which can help in doing more pure functional stuff, because of course, if you're doing pure functional programming, you end up making a lot of copies of things because you're not mutating states. So that can be very inefficient in C++. So there's things like the immer library, which tries to make this actually reasonable to do in C++. So I'd recommend having a look at that. Can we compile the snippets that you show us in which C++ standard? I believe everything which I presented apart from herbceptions should be compilable in C++ 20. I think I tested all of this stuff in MSVC, so you should be able to compile everything there. Slide 68, running max across a range of all negative ints will have an issue with an identity value of 0. Oh yeah, sure. That's the this one. You need to change the identity element. Yeah, sure. A developer's already done the kind of the work of checking whether a specific type follows the laws of monads or monoids you laid out or alluded to using type traits. I think that that's not generally possible in C++, like because type implementations are so often subtly different, and we don't have a built-in method of exposing whether something is associative, things like that. We don't have a programmable and queryable way of inflicting semantic constraints on our type's behavior. Like we might get contracts in C++ 23, which are useful for checking semantic constraints, but we wouldn't have, at least that I've thought of, something which really makes it easy to work out some things like associative and whether it behaves in a way which conforms to the functor or monad laws. Do you think coroutines could be expanded in a backwards compatible way so that they would be equivalent or as expressive as do notation? I honestly have not looked into that enough to be able to answer that question. Like intuitively, I'd say that if we had exposure to the subfunctions which are generated by the compiler, then you would be able to like jury rig something for most monads. But I haven't considered whether it would be general enough. Is my dynamic polymorphism talk the same as the one that's already on YouTube? Yes, if you've seen my dynamic polymorphism talk from Pure Virtual C++ a few months ago, then you've already seen the talk I'm going to give tomorrow. Given you reference many interesting libraries, how do you know if you can trust they're high quality / going to be maintained? I mean, that this is the eternal sociological technology question, right? Like, how do we know if something's going to be maintained is a question which you have to ask yourself about what your constraints for your business are, and is why having some of this stuff in the standard really helps. If you're using third-party libraries, then you have to take into account that they might not be maintained to the same level of standard or for the same longevity as the standard library. In the code examples was pipe and then for the optional, some third-party library. If it was, where can we find it? So the pipe and then, I think the Vittorio's skeletal library maybe has that. My implementation of std optional, TL optional uses dot and then. I use the bar and then in this talk because it's more in line with what ranges does, and I wanted to have that nice like visual symmetry. But it's a very similar. It's very similar to the dot and then. You can implement it in a different way. Actually, using pipe and then instead of dot and then avoids some very obscure issues to do with how SVNA unfriendly callables interact with member function overloads, which is a lot of fun, and you can talk to me later if you're interested. But I think I worked through all of my questions. Thank you so much for all of those. It makes up for me going a little bit fast on the talk, so we're about out of time. So thank you very much. Please come chat to me, either just grab me at the conference, find me at the expo hall, wherever, and enjoy the conference. Bye.